Okay, so this is what we'll talk about, pitch estimation. So this is what we started off with last time, right? This is a simple sine wave or cos wave, but it's a simple sinusoid that we have. And the goal is to find the frequency or the period of this signal. Now, speech signal is nothing like this, but if we make multiple assumptions, then we can think of speech signal as a sinusoid or a combination of sinusoids. So let us start with this basic example of detecting the period of a sinusoidal signal, and then let's see how we can take that forward to a more complicated signal like speech. So that's the goal. Okay. So let me just pause for a minute. Okay, so the period is basically from this point till this, or it is this point to this, or it is the peak to peak, or valley to valley. So there are multiple ways in which you can get the pitch period for this signal, because this is a well-behaved signal as far as periodicity is concerned. Right? No matter what two points you take, uh, two well-chosen points, you will get the same period because it's a nice sinusoid signal, right? And the idea of taking multiple such values, last time we discussed this, was you want your decision to be robust. So if there are 2 points that you choose, which are slightly off, that is compensated if you take two other points, right? So for example, what we saw last time was if you take these two peaks and you get some x value, and if you take these two values and you get x plus delta or x minus delta, then you have that much more confidence about making a better estimate. And the example we took last time was when a friend is trying to go to some other friend's house and he's trying to figure out what the distance is, he or she will ask multiple people so that there is no over reliance on just one estimate, because that's what we do in real life, that we ask multiple people or multiple detectors for a particular value if we are not confident of one person giving us the right answer, right? So that is the logic we are applying here also. Clear? Okay. So then the first thing we saw last time um, was that we take the peak locations and their amplitudes. So in this case, we have two peaks, one here and one here. That's our one estimate, right? And then last time we talked about the second estimate as the valley locations and amplitude, right? The way this figure has been given in the book and the way I got it, it's slightly arranged in the different order, but it should not matter. Right? It doesn't matter if I ask Bhargav first and then I ask Nida, or I do change the order. The answer will more or less be the same. Well, actually, it will be exactly the same because these are independent samples that I've taken. Okay, so that is the first. The second is I take the peak amplitude, that is this guy, and I take the previous valley. Okay, so the peak amplitude here, the previous valley, and I add those values, the amplitudes, right? So, so I have this guy plus this guy giving me something much bigger. I have this value, and assuming the signal is continuing here also, I have this value. I add those amplitudes, I get a bigger value. Right? So those are my two estimates. Is this clear to everybody? Okay. Then the third is I take the peak and I subtract the previous peak value from the current peak. If the value is less than 0, that is if it's negative, I make it 0. If not, I'll keep whatever value I get. Now the reason I want to say this is in real life, you might not have a sinusoid which is exactly like this. Last time I drew a sinusoid which had amplitudes varying, right? And so if that happens, if the current amplitude, if the amplitude of the current peak is smaller than the amplitude of the previous peak, then you have x minus something that is bigger than x, you get a negative value. You don't want any negative value, so you just make it 0. Is that clear? Okay. So these are the three values that you've gotten from peaks, right? Let me just go over it once again. What we have are peak locations and amplitudes in the first case. In the second case, we have peak amplitudes and the previous valley amplitudes added, right? That's the second. The third is you have the current peak amplitude minus the previous peak amplitude. If that difference is negative, you make it zero. Clear? That's clear to everybody? Okay. So now, who can tell me what the other three are? Naveen, let me, huh? Yeah.
Amplitude of valley
Okay, that's one.
minus the previous.
That's one. So we'll come back to you. So that's the fourth. Okay. Kavya, you were saying something. So that's the, he has told us about the fourth value, which is valley, location, and amplitude. What is the fifth? Yeah, tell me. Yes. So here we had peak amplitude minus previous valley. Now we have the valley amplitude minus or plus, it doesn't matter. We are essentially looking at amplitudes, right? So valley amplitude plus the previous peak. And so you get a much bigger value. Is this clear to everybody? What we've done? It's exactly the opposite of what we have done for the peaks. So all you have to do is really remember what we are doing for the peaks and then do the same thing for valleys. I say it's opposite because the amplitudes are now changed. Clear? And the locations are now, instead of being on peaks, they are on the valleys. And then the last one is the valley amplitude minus the previous valley. And in a perfect sinusoid, that value will be zero because the peaks and the valleys will always be equispaced and their amplitudes will always be the same in a perfect sinusoid, right? So you get these six values. Is this clear to everybody? This is what we covered last time, but I thought we'll cover it again a little more systematically so that everybody remembers this. So six things we have done, right? Bhargav, start with the first. Okay, Divya. Okay. Okay, it doesn't matter if the order is off, but as long as you remember what we are doing. So the first one is the peak. Second is peak minus or minus the previous peak. If it is less than zero, you make it zero. What is the third? Okay, minus or plus, but as long as the value is up. Okay, what is the fourth? Just the valleys and their amplitudes. Fifth, sum of the current valley and the previous valley. Okay, valley amplitude minus previous valley amplitude. If the difference is less than zero, you make it zero. Okay, so those are the six values that you get. Kaustav, we're just revising what happened last time, and I'll give you all this video also. So, okay, so those are the six values that we have. Now, what we had discussed last time was that sinusoid is a very simplistic way of looking at a speech signal. In real life, that is not the case. So now let us see what happens when we make this a little more complicated. So this is what happens. So now this is some sort of a speech signal which is filtered a lot. And I'll tell you what that filtering is. But assume that you had a very complicated speech signal, which was the full 0 to 4 kilohertz signal, right, which was sampled at 8 kilohertz. So the highest frequency was 4 kilohertz. What you did was then you filtered that signal quite a bit. And what came out was this sort of a signal. And now the question to you is, what is the periodicity of this signal, or what is the pitch frequency or pitch period? That's the question, right? So, what is the first step, Kaustav? Their amplitudes, right? Okay. So peaks are always positive. So, okay. So, I mean, assuming the signal is or valleys, yes. Assuming the signal is, DC offset is removed. So what we have, the first signal or the first way of deriving the pitch is all the locations and the amplitudes of the peaks, right? So these are the places, right? And then, uh, Naresh. Yeah, so what have we done? We have this peak amplitude minus the previous value. Very good. So what we have is this. So let's take this example. This minus of this guy, which is minus of minus to plus, or simplistically the sum of the amplitude and this amplitude. Okay, so that's this guy. Again, here it is this plus the amplitude of this plus the amplitude of this. So we get second set of impulses. Clear? Okay, now who wants to go for the third? Divya? What is this third signal? No. Yes. Yes, good. Eh, Right. So that's why what happens is here at this point, this peak is smaller than this peak, right? So when I take the difference, it is negative, and so we have made it 0. Clear? Here, this amplitude is higher than this. So when I take the difference, it is positive, and so I retain that value. Clear to everybody? Yeah. Similarly, here, this peak is smaller than this peak, and so when I take the difference, I get a negative value. I make it 0. So those are the three estimates that we have gotten. Right now, before we go into these three, what kind of periodicity estimates you can make from this signal? Who wants to take a guess? Nida, do you want to? Is 2 is increasing across what? So the question is, given that there is M1, M2 and M3 as three signals which are estimating the period of the signal, what can you say about period estimates from M1, M2 and M3? Is there anything you can, any statement you can make? Kavya? Yes. Okay, that's yeah. So you guys are on the right track. See, what is happening is because we did not consider a complete sinusoid. I think that's what you're saying. So because you're not looking at one sinusoid, which is a good, nicely well-behaved sinusoid, we get a lot of complicated things happening. So for example, in this case, if the period was between this point and this point, then in this case, it is twice as much, right? So these three guys have given you different estimates. Is that clear to everybody? That's the reason why we are taking multiple values. Clear? That this person or this method had given you, let us say, x1, x2, x3 as your period estimates. This will be exactly the same, x1, x2, x3. But now what this is doing, and x1 and x2 are roughly the same, maybe delta difference here and there. But M3 is now telling you that it is x1 plus x2, which is roughly twice as much, right? And so that's why it's important that you take multiple such values or multiple such methods of computing the pitch period, because one method might really be off. Is that clear to everybody? And this is a classic problem in pitch estimation. It is called halving and doubling. I don't know anything about this pitch signal, right? If I'm given these three estimates, for a minute, forget these 4, 5, and 6. If I'm given these three estimates, only one of them is correct, right? Only one of them is correct. It's either M1, M2 or M3. Now let us say M3 was correct and I went with M1 or M2, then what I have done is I have doubled the pitch. My pitch estimate is now double. So that's called a doubling error. If on the other hand, the correct value was M1, M2, and my estimate, final estimate was M3, then I have halved. Right? So that's a halving error. Otherwise, if you make a mistake of about 4 or 5 hertz, it's okay. Nobody really is bothered about that level of mistake. In real life, if I say that the actual pitch value was 102 hertz and my estimate was 99 hertz, it's okay. 3 hertz is tolerance of 3 to 5, actually plus to minus 5 hertz tolerance is okay in real life. But halving and doubling makes a big difference. Why? Who can guess what happens if you do halving? Or this is out of syllabus, but I want people to think about what happens if the pitch is halved or doubled. And we've covered this last time. Very good. Very good. Right? So if the pitch estimate is 100, then we say it's most likely a male. But if the actual pitch was double, just 200, then it's actually a girl. So you've made a big mistake. And similarly, if the reverse happens, that's also equally bad, right? So that's why halving and doubling are big problems in real life. You don't want those mistakes. But 3 to 4 hertz plus 5 to minus 5 hertz, it's okay, because that still does not change your final analysis drastically. Clear? So that's why you take multiple values. Are there any questions so far? I'm trying to go very slow, so don't get bored. But if it is fast, let me know. Clear to everybody what we've done? We've taken 3 samples, and what I've shown is that by taking these 3 samples, you get 2 different types of estimates, and so it's really up to some analysis to now figure out which of those is correct. And it's possible that even after doing a lot of this complicated analysis, your final answer may be wrong. But that's something we have to live with, because that's what real life problems are, that you will never get 100% accuracy on the problem you're trying to solve. But at least you're trying to reduce that error. Clear? Okay. So now let us go to the next 3 cases. And again, these 3 are exactly the same as this, except the peaks are now replaced by valleys. So Megha, what is the 4th? What is this case? Amplitude of the valleys, right? So we have this valley, this amplitude, this valley, this amplitude, here, 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 and here. Santosh, what is the 5th? Slightly different. So we are looking at the valleys now. So it's the current valley plus the previous peak. Otherwise, you might get a negative. It's only when you go from valley to peak that you are assured of not getting any negative, because you've taken the amplitude of the valley and amplitude of the peak, and they'll always add up. Okay. So what we've done here is this valley plus the previous peak, this valley plus the previous peak, this valley plus the previous peak, this valley plus the previous peak. Okay. These are 5. Bhargav, what is the last one? Right. And if that difference is negative, you make it 0. It's possible, right? Because the value is negative, the previous value is also negative. So it could be that the difference is less than 0. In this case, it's not happening because this value is higher amplitude than this. this valley is higher amplitude than this. Oh, well, this is happening, right? This guy is 0 because this value was smaller than this. So the negative was 0. So it was negative and so you made it 0. Is this clear to everybody? So we have 6 values now, 6 values or 6 estimates of what the pitch period is, right? And the pitch period basically then is just the difference between these guys averaged out. So this could be x1, this could be x1 plus or minus delta, this could be again x1 plus or minus delta. They'll not be drastically different. So it won't be that x1 is 80 and x2 is 60, right? x1 is 80, x2 will be 80 plus or minus 3 or plus or minus 4, right? Clear? Now, I think I have the next slide also on what we do. Yeah. Oh, I wanted to make this animation. Okay, you know what? Give me a minute. Okay, so we're back. Okay, so what we have now from the previous slide was all of these values, right, that we had. Now what we do is we take each one of them individually. So let's start with M1, right? Let's start with M1 and figure out what the pitch value is. The crudest thing to do was to take the difference between the consecutive impulses that we had and take the average of those differences and say that that is the pitch, right? But we just saw that that could be a problem because of halving and doubling. So you have to do something else on top of it. Is this clear to everybody? Why we have to do something on top of just taking these pure values, right? Okay. So one thing that we do is we start with what is called a decaying exponential. And I will explain what I mean by that. Again, there is no maths in this, but everybody knows here what an exponential function is, right? Give me an example. Ashraf, Abdul, e power x, right? Now, if I say x is positive, is that decaying or increasing? How many say increasing? How many say decreasing? Right. So if x is positive, e raised to x is going to go up. It's going to exponentially grow. Right? Is that always true? Think about this. There's a trick in it. Anyways, want to guess? We thought about this during the energy calculations. Good. Good. Okay. Because if it is less than 1, then you get into some trouble. Okay. So now what you do when you want to decay it is you do e raised to minus x. So it becomes 1 over e raised to x. The values keep going up. Right? Still increases. I'm just confusing you all. Because the E value is not changing. It's the X value that is changing. In energy, what we saw was if the X is changing, then the exponential changes. Tricky things. Oh, you're, no, 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 let me pause. Okay, I shouldn't have. Okay, so we have this guy, right? Let's take this one of these. And what I want to do now is go from those train of impulses, loosely speaking, that's a train of impulse, right? From those values to some good estimate of what the pitch period is. That's the goal, right? Now, if I go with all the values as it is, there is a halving or doubling problem that happens, right? And so what I do is I have some cooling off period or what is called as blanking period. So I start with the first peak. Then I say that I will not detect any peak for the next X samples. Is that clear? What we are doing? We start off with this peak here, and then we say, no matter what value of peak I get, or no matter what value of the impulse I get, I will ignore it for a few samples. What am I gaining by doing that? Huh? Yeah, but what am I gaining by neglecting the peak? Yes, but yes. So what you've essentially done is you are forcing your pitch period to be not less than a particular value. You're saying once I find a peak, I will ignore all the peaks for the next X samples, which means there will be no two peaks which will fall within that X sample, which means you are saying that I'm trying to avoid the doubling problem. Is this clear? So understand the concept first, and then we'll figure out how to answer this in the paper. But understand why somebody is doing this kind of a work. You start with one peak, and then if I did not have this cooling period, I might get the next peak very quickly, right? And then my pitch period is very small, my pitch frequency is very high. So to avoid that, I say I get a peak, I will do nothing, I will not get any peak by force till a certain time has gone by. This clear? That's the reason, that's the justification for doing this. Yeah? That is one step. The next step you do is, even after that has happened, there are some peaks which are of low value. There are some peaks which are of low amplitude, like we saw here. There are some of these. Now these could be coming from some noise, or they could be genuine peaks. You don't know that without doing some complicated calculations, whether those peaks are valid peaks or what are called the spurious peaks. Spurious means wrong. So spurious is a word that is very often used in speech analysis. Spuriousness is when something is cropping up without any reason, without the right reason, right? So what you've done is, first step was you took the first peak, no matter how small or big it was, you took the first peak. Then you said I have a blanking period or a cooling period where I will not get any peak at all, no matter what. So you went till some time, right? It's called the blanking time in book, but it can be also cooling time or whatever. So let us say that that time was tau. Then one option you have is, okay, now whatever peak comes, I'll take it, right? But the problem with doing that is, if a peak is of very low value, you could be in trouble because you have taken a wrong peak as a pitch estimate. So what you do is you start off with a decaying exponential. So from this point, you say I will start a decaying exponential, right? And that could be e raised to minus x, it could be 2 times e raised to minus x, it could be 10 raised to minus x. We don't know what that exponential base is, but it's a decaying exponential. And what that does is, any peak that is less than the value of the exponential is ignored. Clear? Clear what we've done? Any peak that is less than the exponential value is ignored. We say that that is not a correct peak, that's a spurious peak. So essentially these two steps, 1 and 2, have helped you remove peaks which might not really contribute to the pitch frequency. Clear? And then as this is decaying, you go on till you find a point where the peak is higher than the exponential, which is this guy. And then you say, okay, so now this is a correct peak, which means this peak is an estimate, a likely estimate of pitch period. Clear what we have done so far? Two things we have done. One is we have had some blanking time to force that no two peaks can be close enough. Second thing, so there was no amplitude in this. No matter what the value was, we said it's not of any interest to us, we'll just not take it. So that is one, based only on the distance. The second is based on the amplitude. No matter what time difference it is, if the amplitude is below a certain value, you will not consider it. And that certain value was computed using a decaying exponential. There are two things happening here. Clear to everybody? And so what you see here is after that point, there is a big peak which is above the threshold given by your decaying exponential, and it is also beyond the blanking time. So it meets both the requirements. And so you say, okay, this could be a likely contributor to pitch estimation. So that's your second peak that you take. Now again, you go to this guy and you start your blanking time, cooling time, and then the decay, right? So we do that again. Now again, no matter what the value is, you are ignoring it. Then this guy was less than the exponential value. So you went on till you found a value which was above the exponential, right? And then you continued. There was a blanking period. And interestingly, what you see is that in this blanking time, there was a impulse which had a much higher amplitude, but you're ignoring it because you have forced yourself not to look at two values which are close enough, which are close to a particular threshold, right? Is this clear, Kaustubh? Question? Huh? This is a peak. No, say that again. Yes. Huh? Yes. Yes, so it doesn't matter. So if I understand your question, Kaustav and Bhargav, hold on. If there's a question, you can, huh? Okay, after this, so listen to what he's saying. That's also an important point. So if I understand correctly, what you're saying is if this peak was here, huh? Is that the question? Okay, what would happen in that case? You tell me. What would happen is if this peak was moved here, and I'll keep my mouse here just to show what it is, mouse pointer, right? Okay, here. Yes, if it repeats after the blanking time and if it is above the exponential, you will take it. So let me draw what you're saying. So here your exponential had come down and it started rising because this amplitude was there. Now you have a blanking period and then you again have a decay. Now in the figure that is there, there was an amplitude here. And we've ignored this because this is within the blanking time. Now, if I'm right, your question is, what if there is an amplitude here? Is that the question? Huh? Okay. Exactly after the blanking time. So let's say this is where? Yes, absolutely. So what does the algorithm tell us? So think of it. So the reason I want to sort of stress on this whole method is this is algorithmic thinking. You're thinking from an algorithm point of view. What are the steps I have to follow? It doesn't matter how logical or illogical they are. Somebody has given me a set of steps to follow. I will follow them. So in this case, so let me remove this guy. So you start off with this peak. You come to this value, right? You've changed your exponential to here. Now you have a cooling or a blanking period. So you are now blanking. Okay, you're going on and on and on and on. You see this value, you're like, no, this is in my blanking period. So no matter what the amplitude is, I'm going to ignore it because time is the criteria. Then you come here, and then suddenly after your tau time has expired, the blanking time, what does the algorithm say? You will immediately start with a decay, exponential decay, right? Some y raised to x. We don't know what y is, we know x as the samples. And now what you're saying is immediately after that, you get a pulse. That's fine. The algorithm says that as I'm decaying, if I find some signal, some peak that is above the exponential value, I will take it. So then what happens is you go up here, again you have a blanking period, again you start. So now again it's possible that just while you are decaying, you find something big, right? Then you go up and then you start. Huh? At exactly at this point, there is an amplitude here. What does the algorithm tell us? That you will start decaying, right? But if the amplitude is above, you start with it. You go with the big guy. It will not decay. It will just go up. Because the algorithm says I will stop looking at values for tau time, which is the blanking. Once that time is over, I will start decaying till I find a value that is higher than the decay value. If that happens at the first point, so be it. If it happens at the first point, I will not start the decay. I'll just go up. Clear? This is clear to everybody. What was your question? Yeah. Blank again? That's a good question. Okay, that's a very good question. So, and that's where you get into what are called the pathological cases in any algorithm, or what are called as the boundary cases. So let me explain that. That's again out of syllabus, but if you're getting into some algorithmic work as higher studies or any of your jobs, it's important to know this. So the question, let me just repeat it, is if I have a blanking like this, and then as I start decaying, this is what I should have done, right? And then I get some amplitude here, I come here, and then as I come here, this is my tau time. I want to now start decaying from here because I haven't found an amplitude. But I think what Bhargav is saying is I find an amplitude exactly here. No? Okay. Okay. Okay, I'll come to that. So this is also a boundary case where your tau is over, right? And the amplitude is also equal. Now what do? Do you continue with the blanking period or do you start decaying? You don't know this because I have been very vague in explaining the algorithm at this point. And that's where when you code this in MATLAB or whatever your favorite language is, you have to be very accurate. And that's when you start writing the equations, you have to be very accurate. So my thing was x of n to n plus tau is 0. I forced it. Huh. I could say that then the exponential decay has to be has to be less than x of whatever j it is, right? If I say it has to be less than or equal to, then my problem is solved. Then I can make a very exact decision. You see what I'm saying? If it's at the boundary, then you don't know what it is, and that's when you have to you have to think of those boundary conditions and say what you will do. So in this case, I don't know what the algorithm will do because I don't know exactly what I want to do at that point. So when such a case comes, you go back and check your algorithm, and then you say, okay, if that is exactly equal, then I have to make a special case in my algorithm. That if this is exactly equal to tau, clear? And if the amplitude is also exactly equal, then I just write an if statement because that's a very special case. And I say if that happens, I don't know what decision I will take, but let us say my decision is to go down, go the exponential decay path, then I will do the exponential decay. Or if my decision is to continue with the blanking period, I will continue. So I think your question now is here. Again, the same thing. We don't know. It depends on what the equation is. right? The book does not talk about that, about the boundary cases. So you can make an assumption about the boundary case. Yeah. So you can say that, okay, the exponential decay has to be always less. Only then I will go up. Or if you say it has to be less or equal, then it's fine. If you make that assumption that it has to be less or equal, then you say, okay, I found it, now I'm going to continue. Clear? So these are boundary cases. This clear to everybody? You as an algorithm developer. Yes, that's a good question. So, okay, so we're getting into a little bit of out of syllabus kind of discussion here, but this is interesting. As analytical people, we should be thinking about these things. So let me pause this. Start. Okay, so now I don't think I have anything else. Yeah, oh, okay, yeah. So then you keep doing this. So at this point, again, I get a peak. I sort of have a blanking time, and then I, start my exponential decay. The value goes up. I get the value. I get that as a valid pitch estimating peak. Very good question. As an algorithm developer, you have to tell me what it is. Who can guess? That's a good question. I'll answer it. But who can guess whether it should be? Don't worry about what the book says. It should be variable or should not be. How many say it should be? No, how many say it should be variable? 1, 2, 3. And everybody else says it should not be varying. So you are saying it should not vary. Okay, so 1, 2, 3. No, only, oh, Santosh, yeah, why do you think it should vary? That's fine, it can be wrong, it's okay. Depends on the. Okay, think about it. If you think of a good way of saying it, let me know. Yeah, Abdul. Yes, that's a good answer. Right. So deciding criteria is, so his answer is right. Your answer is still can be improved upon. Wait. Let him answer. Wait. Shh, hold on. Let him answer, and then I'll come to Megha, and then Kavya. Okay. Okay, but within a speech signal. Okay. 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 Okay, so you're agreeing with what Kaustav is saying. What about you? Mhm. It should be constant. Okay. Okay, so everybody is agreeing. Okay, so this is an algorithm development, right? So there is no right or wrong answer, right? There's only logic which you can use to defend your answer. The better the logic, the the better you can defend your answer, and ultimately you will get better accuracies. So the litmus test, everybody knows litmus test, right? For your logic is how it holds up in real life, and that's where research is, right? Unfortunately, I have to say that you can, and in real life you do change values. The reason is the following. When I'm talking or singing, or whenever I'm vocalizing something, whenever I'm saying something which is voiced sound, my pitch is varying. Right? I never say that Om Deshmukh's pitch is 102 hertz, Abdul's is 108, Kavya's is 195. We don't say that, right? Right. No, 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 no. But the speech signal by itself, by definition, is varying. I never say forever. My speech signal is varying. Ah, come on. So my speech is varying. Oh, that's good. Yes, exactly. Now you're changing your answer. Not type. Okay, yes. So in that window, yes, in that window of analysis, let's say you take 30 milliseconds of window, in that window, that tau value will be the same because that's just too much complication. But when you get some estimate in that window and then you move to the next case, you have all the choices to change that value based on what the pitch estimate is. Because in the beginning, I don't know if it is Kavya or Ohm, which means I don't know if it is 200 hertz or 100 hertz. So you just make some assumption about tau for the first 30 milliseconds. You come up with some value, and then you say, okay, in this case it was 195, so my tau should be now proportional to 195. Suddenly, what you see is it has gone from 195 to 230 because now Kavya is really screeching. Right, 195 is low pitch. When you really go at high pitch, it's like screeching. And then you want to now change the tau value to accommodate that change in pitch. And then you again see that the pitch has come down. Again, you change the tau value. For a window, it will remain the same. But as you move from window to window, you should change it because otherwise you are not learning or you're not using what you've learned from the previous pitch analysis that you've done. Clear? So that is where the dynamic nature of speech makes your life much complicated because things are changing very rapidly. You have to learn something accurately, but not only that, you have to now use what you've learned in your next analysis also. And again, you have to do that in a smart way. Clear? Clear to everybody? Does that you had the question, right? Okay. Yeah. Oh, high five. Okay. So clear, right? So think about these things. I mean, and then you can easily think about ways in which this algorithm can be improved. There have been a lot of improvement papers that have come out on this algorithm also, right? There's one question that we have not answered, which is out of syllabus, but I want you to think of. What exactly is the tau value? People have asked me, can you change it or but what should be the tau value? Okay, that's like a very conservative estimate, but yes, accurate. I mean, that's correct. That it has to be really less than the pitch value. But if you were to really push the limit, where would you push it to? थोड़ा जोर से. Less than one. No, 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 no. After him, it is Kavya. Less than one of what? Less than one. Okay. You think about it, Kavya. Hmm? Sort of on the right direction. No, no, no. It's his turn, and then his turn, and then your turn. Yeah, Abdul, quickly. What did you have to say? Okay. Yours, Kaustav, you had something to say? Huh? Right. So we don't know the pitch values. We don't know the pitch value. We don't know where it starts. Yes, we don't know any of those. We have no idea. And that's where the algorithm gets really complicated, right? So everybody is trying towards the correct answer. Huh. I'll answer your question, okay? right?
So we take that, get an average of it, and then take 20% of that and take an average.
All of what you're saying are very valid answers. And it's only when you start with some assumption, you run your algorithm on 5 speech signals, you see it makes mistakes somewhere, then you go and change the algorithm. You figure out some boundary cases, you go change the algorithm. And then you test it on a bigger database. But the rule of thumb, and I'll come to your question in the end, the rule of thumb is if the pitch estimate is 100 hertz, then you know that it is going to vary between maybe 80 to 120. See, we as humans are producing speech using our vocal apparatus, which has its own limitations, right? For example, as a human being, my limitation is that I cannot run beyond, let's say, 20 miles per hour. I cannot move beyond that speed. So if I was spotted here at time X, then at time X plus 1 hour, the radius in which I can be spotted is only 20 miles from here, right? Because that's the limitation of my speed. Similarly, when vocal folds or when the vocal apparatus is moving, if I have said something now, like if I have opened my mouth and said ah, then before I can go to S, from ah to S, it will take me 20 milliseconds. So that is a limitation that is there because of my physical abilities. Is that clear to everybody? So we use that knowledge of the system to make some estimates. So similarly, if I know that the current pitch is 100 hertz, then the limitation of vocal fold says that the next pitch period, it cannot be 200. That's just not possible because the physical limitation of my system will not let me change my pitch that quickly, right? It will take some ramping up time. So the tolerance is about plus or minus 10%, plus or minus 15%. So if my pitch estimate is 100 hertz now, I know it cannot be 50, right? So it goes back to what Megha was saying, that it can't be too small, right? So the window is really, you can make it very small, but I'm trying to make it as big as possible, and that will be about 70%, 80% of what the value is, of what your initial estimate is.
Basically, you're starting off with a guess and then you're.
Yes, yes. So that's a good question then. So if your estimate is 100, then you have 80% of that, which is 80 hertz. So the window is around 80. But if you are starting at the beginning of the world, which is beginning of the speech signal, you have no estimate. Then somebody has to tell you that this is a human voice and not a dog barking or not, not a bird singing a song. Yes, that's a good point. That's the point I was going to make now. That the first time you'll always make a mistake. It's like you're learning to drive. The first time you're learning, your mind has not come up with the algorithm of how to hold the bicycle, right? So your mind is also now you're training your mind with the algorithm that you have to, balance your weight like this and then pedal and all that. So the first 5 times you will make a mistake. But then once you learn it, you've learned it, right? It's very much like that. The first 5 samples, you will make a mistake. And that's where you use some estimate of your knowledge. So you say that, okay, this is a human speech. So I know the lowest pitch is 80 hertz. The highest is 250 hertz. So my tau value will be in that range. As I move 4 or 5 samples, I'll be able to get a much better estimate of whether it is a boy or a girl, man or a woman. And then I'll use that estimate in my next samples. And then as I get better values, I will then even, sort of further tune the value of tau. Is that clear? So these are all algorithmic complications. These are all algorithmic complications. You have to live with this in real world. That when you start building an algorithm, you come up with some assumptions, you try them out on MATLAB or some data, and then you sort of move with improving the algorithm. Clear? Okay. So now, question? No. So now we have these values that we have come up with, right? So in this case, we have this one sample, this second, this third, and fourth, right? So we have those four values. We do the same blanking followed by decay for all the six samples that you had here, right? From all of these six samples, you get different pitch estimates. You just do the average of all of those, and that is your final pitch estimate. So what you have done essentially is, because speech is variable, and that is why speech processing is such an important and still a very active area of research, because the problems are very difficult, algorithms are more and more complicated, and you come up with a better algorithm, you get better paper, you push the research, right? So what you do is you take lots of samples, you come up with some estimate for each of those samples, you come up with a way of combining those. That's your algorithm. In general, for anything in life, take multiple samples, figure out some way of figuring out a value for each of those samples, and then figure out a way of combining those values. Clear? Any questions? Huh? Okay, let's quickly summarize the method, because that could be a 20-mark question. I mean, in 1 year's question paper, this was the only question that was asked in Unit 3. Okay, describe, and then you have to really write a long story if it's for 20 marks. Huh? You won't? Okay, well, 10 marks at least, right? 8. Really? Oh, wow. Okay. Yeah, yes, you should write. I told you this, right? I mean, based on who is asking you, you have to give you have to give appropriate answer to. So I'm preparing you for a lot of these worst things. Okay. So let's very quickly revise the algorithm. Ashraf, start with the first thing, and everybody just tell one line. Okay. You will be the last guys, but oh, I can make it random. Okay, Abdul. I mean, loudly. Okay, so considering the peak or the maxima. Kavya, next step.
Peak of the pregnant signal minus
Valley's value at the previous valley. Okay. What's your name? Prakash. Third. All of you think, okay, and pay attention to what he's saying. Next, okay. Bhargav. So he didn't give the answer, so you tell me the third step.
The present peak and subtracting it with the previous peak.
Very good. And if it is less than 0?
Approximate it to 0,
Make it 0. Okay, third. Divya, fourth step. Okay, magnitude of the valleys and their locations. That's fourth. Mega.
magnitude of the present value plus the previous peak.
Previous peak. Okay. Santosh. Pay attention, Bhargav. It's minus, right? So the magnitude of the first value, current valley minus the previous valley. And Nida, what happens if it is negative? You make it 0. Okay. Kaustav, why do we take these 6 values? Why not just one? Right. You need more samples because the speech is varying. Right. So you need more samples. That's why you take many of these. You can actually go from 6 to 60. You can come up with many different ways, but the algorithm that is mentioned in the book talks about 6. You might as well come up with something totally different also. Right. Okay. Who's left? Kavya, you didn't say anything yet. Right. What happens next? You got these 6 values. What do you do next? Really? Divya, what do we do next? Very good. Okay, so you take the blanking time. You don't average it, right? So you take the blanking. Yeah, after the 6, what you do is you start with the blanking, right? Okay, what do you do after the blanking, Naveen? Who's Naveen? You are Naveen.
Taking the signal after blanking,
Huh?
certain period of time we are neglecting the signal.
Okay, good. Sorry. You're saying something important. Yeah, go ahead. After the blanking period?
We are neglecting the signals.
Till the banking period is over, not after. So till the banking period is over, guys, pay attention. Till the blanking period is over, you neglect
and start the
even if the amplitude is high. Okay, stop. Santosh, what happens next? So exponential decay. You could do a linear decay also. That could be a new algorithm. And who knows, this guy who wrote the algorithm might have tried it, right? He might have started with a blanking period and then started with a linear decay and then maybe realized that that doesn't work well. So he went with exponential. That's the way you come up with algorithms also, right? Okay, you do this. Then Kaustav, what do you do next? You're starting with the decay.
after that we have to check if there is a amplitude value depending on your algorithm is equal to or greater than value. If it's more than that, then the blanking region starts from the amplitude of the high.
And then what do? You keep that peak. You keep this peak that you have found. Okay, that's important.
For a specific amount of time
Right.
decided by you, and then you again start the
Okay, Bhargav, what happens next? That's correct. Bhargav, what happens next?
Then again, we after the blanking period, the decaying start. Even during the blanking period or during the blanking time, if there's a higher peak, it neglects it. But during the decaying time, when encounters peak higher, again it changes to the peak value and again starts.
Right. Okay. So you keep, yeah.
Doubt in this. The decaying value, I mean, the amplitude we're looking basically depends on the previous peak value.
Yeah. Yeah, yeah. Here. So you're starting from here and then you're decaying from this value. So it depends on the previous amplitude. Yes. Yes. Is that clear what she's asking? If that value, if this value was much higher, you would have started blanking from here and then your exponential would have decayed from there. Yes, that's absolutely true. Again, the logic is if I'm talking loudly, now before I can actually make it low volume, it will take me some time. I cannot do it drastically.
And the decay, does it depend on the peak value? The decay expression is the same.
It's the same, it's the exponential value. It starts off with a different value, but the exponential function is the same.
Function is same, but the variable, the value.
The value at which you start will be the amplitude where you started the blanking period. The rate is constant. Yes, the rate is of course constant because you're not changing that function. You can come up with a new algorithm that says I can change the rate also, and then good luck because you need many more data points to learn that algorithm, right? Okay, then what happens? Who hasn't answered so far? You haven't, Naresh, right? So what happens? You repeated it. You finished the end of the word. You finished your sentence. Now what do you do? No, not the sentence. End of the window. Sorry, end of the window. Okay. Now what do you do?
taking average.
Yes, very important. You have to do.
I thought that's what he told. He told you repeat it for all the.
Is that what you were saying? Oh, sorry, I didn't hear that then. Oh yeah, so you repeat it for all the six. That's very important. This is happening for each signal separately. Each of those signals, six signals separately. You don't combine them because then it gets messy. So you do this for each of the six signals, right? So okay, sorry, I didn't hear that. And then what do you do after that? After that, you average the values, and what comes out is one single pitch value. Clear? All the steps are clear to everybody? Okay, this can be a question in the exam. I've seen this in a couple of papers. If not for 20, maybe for 8 or 9 or whatever. But remember this algorithm, okay? Everybody is clear on this algorithm now? Nida, you had a question? I think I answered it, but I forgot what the question was. Ah, yes, yes. Okay. So the question is, if you take the window as multiple of pitch values. You don't know what the pitch value is, so you estimate in the beginning that it's between 80 to 250 hertz, let us say, and then you take a window appropriately. Then you get a pitch value. Now what happens is in real life you don't know any of these things, so you start with some estimates, and then you assume that whatever you've gotten at this point propagates to the next window also. And then you typically don't change the window length. It gets into many more complications. You keep the window length more or less the same. But then what happens because of that is sometimes you have 3 pitch periods, sometimes you have 5, sometimes you have 2. And that's just that's real life. You have to live with that. So the estimates will be, and that's why you take a lot of these 6, 10 kind of different signals so that it overcomes some of the real life problems about pitch varying and things like that. So there is no good answer for that question. The algorithm developer has to come up with a new way of developing that algorithm. Okay? Yeah.
We analyze it with lesser number of things, like there are 6
Huh.
things here we are considering.
Right.
So is there a way in algorithm in which there are those steps are decreased or
Yes. So if you decrease the number of steps, your accuracy might, I not say will, but might go down. Right. So one example is if you don't do this step, let us say, then there is no way you can get a pitch period which is half. It'll always be double. So you'll always make the mistakes of halving errors. In one algorithm that I had developed 2001, I had used 60 such different measures. Yeah, 60 such different measures, and not just the impulses, but we had done something a little more complicated also, where we had a different way of decaying the signal on each side, not just this side, but also on this. It was a little complicated, but we got some very good accuracies. So yeah, I mean, you look at the signal more and more, with many different signals, and then you think of what is a good way of representing that signal in your own method, and that becomes your algorithm.
but for having a good amount of accuracy, the minimum is
That is not true at all. It can be anything again. This is one method that has been proposed.